Thank you, Josh. Please welcome on stage Maddie Shang.
All right, how's it going, everyone? Hope you're enjoying a good day. So I like to start my presentations with a photo of nature. Some of you may know that I live and work out of my truck, and therefore my view is typically beautiful like this. And one of the reasons I like to show these photos is that it's proven that nature helps us learn, right? So anyways, here you go. So when I was asked to give a tutorial on generative AI, I really struggled. I'm like, there's so much content, there's just so much happening, there are so many of you. Some of you are no doubt ML pros. Some of you may be students trying to enter the field, trying to get your foot in the door. Some of you might not even be, in AI yet. You're AI curious, and you may be creators. So I thought really hard about what I can share with you that would maybe be beneficial for most of you. And this is kind of the game plan. I want to talk about how you can take generative AI, take the latest research, and sequentially get it deployed into production, which ends up with happy users. There's a couple reasons why I think this is important. Right now, with foundational models becoming more and more like commodity, the vast majority of the value being created in the market is actually in taking it and applying to a use case, right? So back in the day when Apple App Store first became a platform, there were a bunch of app and game millionaires. We're actually at the same stage with generative AI. So right now is a beautiful and amazing opportunity for you to get into this brilliant future. So who am I and why am I here talking to you? I have about 6 years of R&D experience in the industry. I've worked for companies like Salesforce, Microsoft, Facebook, but I'm mostly a consultant. What I'm most proud of is actually my work in open source. So like my previous AI colleague in open source mentioned, I built a lot of useful things in open source, including the world's first federated learning library that's cross-platform, iOS, Android, web, and also on a server. I've published research papers and also published publications that's technical. I've also am most proud that I created a lot of opportunities for people like myself and like you. For example, starting Women Who Code data science, building OpenMined education, and leading a number of open source machine learning teams. But most importantly, all that said, I have a lot of data about success and failure, so that's what I'm here to share with you today. So this is just another photo of me gathering from the land, and this will become a little bit important later. It's a bit of an Easter egg. So here's the game plan. I'm going to go over with you my personal R&D checklist for taking research to production, right? We know there's Agile for software. We know there's design sprints for the product and design side. But this R&D from research to production isn't something that we have figured out. So I'm just going to throw my hat out here and tell you what is my process that I found to be most effective, whether working with startups, nonprofits, or large companies when you have to deliver actual value, right? We're also going to go over a quick generative AI crash course. And we don't have time to go into the details, and I'm happy to do that later on in another tutorial maybe. But what I'm hoping to provide here is a high-level intuition, right? I find when I'm reading paper or going to a new field, if I have a rough idea of what the frameworks are, what the big pieces are, what they're kind of doing, it helps me make progress when I'm reading code and reading papers. So hopefully that's valuable to you as well. And finally, this is very ambitious. I just had an environment error that I had to fix, so hopefully it's still working. We're going to build and launch a product live with generative AI, and we're going to use free open source AI tools, including Hugging Faces and Google Colab. All right, so are we ready for that? Cool. All right, so let's talk about the effective R&D process for AI. This is my personal version, and it's actually very easy. You just have to answer these 5 questions, all right? Don't need to take photos. This slide shows up over and over again, and you probably have access to the slides after. So the first question is, do we need AI, right? Right now, I work for large companies, and I consult with them. When I talk to execs, there's a kind of like a fear of missing out, and they want to AI all the things. But I'm sorry to say, AI rarely changes product market fit. So you have a struggling product, just slapping some AI onto it is probably not going to make it take off. So the question I like to ask myself here is, what is the simplest version that I can ship? And this is a good way to avoid ROI failures, right? There's a lot of companies spending a lot of money on AI, and it never gets deployed, or if it's getting deployed, it's not getting adoption. So that's why a lot of companies will see kind of like risking, working on AI, and that's why this checklist and this process really helps, right? One of my favorite tricks here is called Wizard of Oz. So what I do is I build a normal user interface, and I get the user to, kind of interact with the interface. But I am the AI on the other side, and they just don't know about it. What I'll do is I'll, randomly screw up a couple times. I'll do a good job a couple times to get a sense of like how good does this AI need to be for the users to find value in this so that we'll actually engage, right? Because if a user is actually engaging with your AI, then they will be able to provide data to help you improve your AI, right? That will be important later on as well. So if that is a red flag, AI doesn't change product market fit, what will be a green flag, right? Typically, AI will be a good choice or something you can consider if you can use AI to 10x something, right? Either reduce the pain or improve the speed or reduce the cost by 10x, or it's augmenting existing human behavior. Anytime you see a human already doing something and AI can help them do it better, then that's a good sign, right? So think about it when something like that happens. So okay, we've gone through the process. We're like, okay, AI is probably a good idea. So what's next? Here it's very important to define clear outcomes. What do you define as success? And also, what does the data look like? So here we're talking about, is it ethical? What is, what considerations do we need to think about? How do you define success in product and ML metrics? And also, what data are we going to use, right? So in terms of ethics, it's actually rather simple. It doesn't need to be big and scary. Think about three things. Who are the stakeholder groups? And keep in mind, your stakeholders are not always the people that pay you, right? They may be other people not internal to you. Second question is, what is the impact, right? Either good or negative. And you have to think about all the possibilities here. And then what is the feedback mechanism, right? So we are all trying our best. Sometimes we will make mistakes, we will miss things. And the only thing that we have to save ourselves is making sure there is a feedback loop, right? So keep that in mind. Now, the next question is, what does success look like? How do I get a promotion if I do this project and it goes well, right? We need to get that clear up front. So first, I like to define success in product metrics, right? If you're building a recommender system, helping people explore new creators, like if you're ByteDance, you may want to have a metric like top K recall, right? So if you suggest a list of 8 things, how many things did the user actually click on? That's a measurement of success, right? And then translate that into ML metrics. So if your objective is to help users explore new creators more, then one of the possible ML metrics will be top K recall, right, for a recommendation. If you're trying to predict if this is cancer or not, then something like F1 might be a good ML metric, right? But you always have to start with the product metric first. So talk to your product managers. And finally, here is very important to think about your loss function. The loss function in a machine learning model is actually one of the key tools we have to align the models to what you want in actual impact, right? So we hear a lot about AI safety, transparency, alignment. That's where the loss function becomes really, really critical. And finally, data requirements. ML eats data for breakfast. So what data features are we going to use, right? How much data do we need? This is where it's once again important to talk to your human domain experts. One question I like to ask is, hey, if I give you this question or this problem, and you know about the data sets you have available, and these are the ones I can get for you, what would be the first thing you look for? It would be like, maybe I'm asking a doctor to predict someone's life expectancy. Maybe, I want to look at their exercise patterns, their diet, and how much they sleep, right? So you're essentially doing feature engineering for free. You can feed all the data into your model, but it's going to struggle in the first couple iterations to figure out what is important. Don't make your model do that dirty work, right? If you can help it along, give it a warm start, right? So if you don't have data, start collecting data now. And while you're collecting data, your real data from your customers, a good trick I like to use is to grab some open source data sets that's very similar in a similar domain and see what is the curve. How much data do I need to put in for the accuracy to improve by how much, right? So when my real data comes in, I have a very good idea of how much data we need and all that. So now we're on to interfaces. And here we have 2 that we need to consider. One, the most important is the human and AI interface. And the next is the interface between AI and the code, usually the backend, right? Why do we care about interfaces here? Good interfaces allows parallel iteration experiments. And practically, this allows me to go sit away in a dark corner, do my machine learning modeling. The engineers not always knocking on my door, ask me questions about, hey, how's it going? What does the data look like? So this is actually really just helping myself, right? So for engineering, we need to think about inference. What does the downstream application expect in terms of input and also output? Also, how are we going to do the model updates? What about data quality and security? Usually, the best way to experiment with this, unless you're a ML-first company, is just to call API. Call API for some kind of ML model, right? And then on the human side, UX is very important. A lot of the advancements in the large language models are actually from reinforcement learning from human feedback, right? So if you don't have a UX, you're not going to get that human feedback. RL, HF is not going to happen, so we don't want that. So the other thing I like to have people keep in mind is design for maximum information gain. It's annoying if you have to ask the user, hey, did this work for you? Did you like it? What was wrong with it? Most people don't have time to deal with that. But can you collect data in the natural workflow of the user to get that information so you can use it to improve your model later, right? Finally, building guardrails and tools for users. What the model's doing may not be what the user is thinking the model's doing. So if there's a misunderstanding or miscommunication there, they may be using the data or AI in a wrong way that may cause problems. So keep these things in mind. So here's a quick graphic about how much data you need to do different kinds of sequential kind of like generative AI iteration. You need less data on that side and more data on this side. So that's just a quick estimation. Finally, this is my favorite part, right? This is where I actually get to go sit in a dark corner and do my experiments and models and research. So here I like to think about doing things in de-risking order and ROI order, right? So what exactly does this mean here? First, make sure you eliminate the accidental risk, right? Do we have legal approval? Do we have enough data? Is the model going to be fast enough for this application? For a lot of high-frequency trading, the model's not fast enough. You can't be using these large models, right? So once you have verified existential risks, then you can basically start looking to kind of like buying yourself time with low-hanging fruits, right? First, have a model that works. Then you can tell the engineers, hey, I got a model over here, it kind of works, but I think I can do much better than that. That's a much better sell, a much better story. If you're talking to an engineering team or going to your boss asking for more time, more resources, then, hey, I want to try this really crazy idea. I'll tell you in 3 months, and then 3 months later, it may or may not work, right? Then that's going to get a little stressful, a little dicey. And practically, if you're thinking about if you should be paying someone for API or you should be building it yourself, because AI engineers and people who actually know how to work with models are fairly rare right now, hopefully you will all become one of them in the future if you're interested, it's typically a better idea just to pay for API, right? Unless you get to the point where that becomes mission critical. That ML problem becomes mission critical for your business. So soon we'll get there, but for most people and startups, that's not the case, right? And when I experiment, I typically have this set of kind of like candidates on my kind of model candidate bench. So I like to have a baseline model. It's the easiest, most common version. If this one doesn't work, something's wrong with my data or pipeline, right? Don't do anything crazy until you verify the pipeline works. Second is a state-of-the-art model, because I want to do my best for the clients or for the customer or for the project. But you also must have a model that you think is most likely to get deployed. Why is that? A lot of times, the difference you gain from state-of-the-art versus a second, slightly less good model is negligible. But the compute could be 3x, the cost could be 3x, the time, the maintenance, the interpretability could be way worse. So you need to have something practical here. And finally, the most informative model, right? Sometimes I'll throw this one in there because I tend to work on the same kind of problems. If there is an experiment I can run now that would help me make elimination decisions down the road for similar kind of problems, then, and if time and resources allow, I will run that model as well, right? So almost always, I will include a gradient boosted decision tree or a regression model, because these are very reliable, easy to interpret, and a lot of the times, GBDT has similar properties in kind of capacity and representation compared to most standard neural network models. So you don't need to go super high-end, super fancy unless you really need to. Finally, You got your model, it's perfectly integrated with the backend because you did the hard-working step 3. Everyone's happy. Do we hit ship, right? Are we ready? Here, we got to think about a couple things. Can you do the lifecycle management, right? Can you deliver a model? Can you read from a model, aka get predictions? Can you update the model if you get new data? And also, if something goes wrong, can you roll back or delete the model, right? Make sure you have that big, red safety button there. And this is actually a lot of times where the war is won and lost, right? So we know about this AI data flywheel situation that I mentioned before. If you have a good enough AI, then users will use it. And if you did good work about data collection, you will get data. And then you can use that data to improve your algorithm, which leads to more user engagement, more data, better algorithm, better product, right? So make sure you're kind of getting this flywheel going before you deploy. Otherwise, a lot of your work is going to be kind of a moot point. We're trying to be useful here, right? So with models and data becoming more and more common and data requirements being less and less because of many innovative and efficient fine-tuning techniques, this is actually where the battle is lost and won for most companies and most use cases. And finally, a lot of things that you have to consider about observability. This is like the other things in ML ops. You don't have to have all of these, but you have to consider all of these, right? So that's kind of the quick checklist. So then let's actually take it through a real example, right? I have this friend, Bree. She's a farmer, hunter, trapper, kind of a awesome mother of great kids, right? She has a little girl, and she wants to be a vet. And one day she was like, hey, can you show me how to dissect a dead squirrel? And I was like, you're a little young for that, aren't you? But she totally did great. I was a little skittish, but she loved it. But anyways, so Bree has a dream. She wants to create a children's book about nature, right? But her pain point is she's not a techie or she doesn't know how to draw. So what's she currently doing now? She's learning to draw on paper, and she's really shy about it. She doesn't want to show me what she's working on, right? And she's also trying to learn Adobe Illustrator. But the thing is, she doesn't even reply to my emails, So I'm just like, oh, this is going to be a little bit rough. So I said to Bree, hey, what about this thing called Stable Diffusion, right? I can set you up with Stable Diffusion and DreamBoost fine-tuning. And if this works for you, maybe this will work for other illustrators or publishers, self-publishers too, right? So here's the actual text exchange between me and Bree. This is a real person. This actually did happen, right? I'll give you a minute to read it. So apparently this is one data point validating that this is a good idea. Someone is very happy about it. OK, so we all had time. All right, let's go to next. This is where we're going to get a little bit deep, and this is where kind of the high-level ML will happen. So hold on to your seats. If this is not driving with you, we'll get to the fun part pretty soon, all right? So first, let's talk about diffusion. We know about stable diffusion, but what is diffusion, right? Diffusion is the process of taking an image, gradually, sequentially, step by step, adding more and more Gaussian noise. So you go from an image to an image that's pure noise and has no information, right? So you're like, oh, you're destroying photos. How's that useful? Well, we're going to use the original image as the input, and we're going to use the kind of noise kind of as the output. And we're going to train a UNet to denoise, right? Learn how to remove noise. The whole idea is if you can predict what the noise is and you remove the noise, obviously you end up with the original, right? And then so you're like, OK, that's great, but how is this generating anything? The trick is if you give it any random noise now, you will be able to generate you an image that's similar to the original training distribution, right? See, it is generative. So then I want to briefly touch on a few different kinds of models that does something similar, right? We have GAN, which is a generative adversarial network. This was fairly popular about 3, 4, 5 years ago. I don't remember exactly. I've been too long in the field. So what happens here is that you have a generator, kind of hallucinating images, and you have a discriminator. The job of the discriminator is to say, hey, given one image, is this a real image or is this a fake one? At the beginning, they're both not very good. But as the discriminator gets better, it gets a reward for correctly predicting, is this a fake or is this a real one? It's forcing the generator to get better too, right? Because the generator is trying to trick the discriminator doesn't want to get tricked. All right, cool. So then we have another class of model called variational autoencoders, right? The idea is very similar. You'll see the graphs are similar. You take an original image, you put it through an encoder, which actually condenses the information in that original image into a lower dimensional latent space, right? So that's what we call Z here. And then there's the decoder that takes the latent representation, a smaller dimension representation of the original, and try to make it the original again. So how do you compare how well your VAA is doing? Is it reconstructing, perfectly as much as possible, right? And then what's interesting about this is that that Z vector in the middle line contains the most relevant and most important semantic information about this original image, right? And finally, we have diffusion models, which I mentioned. You take original image, x0, sequentially add Gaussian noise until you basically get to pure noise, Z, right? And then you make a model go backwards, gradually, step by step, denoise it, so you can end up with x0, right, the original image. Both of these models will use a similar loss function, basically pixel-wise reconstruction, right? Cool. So then let's talk about stable diffusion. So we hear a lot about this. This model actually made huge advancements in being able to control the model and make photorealistic image generation. So how do we do that? So this is kind of similar to diffusion with the exception of some changes here, right? So first of all, the previous models were working in the image space. This one is working in the latent space. Remember how I said the latent space is a condensed representation, right? Therefore, there's less parameters to learn, which means you need less training data, right? The other thing that's also interesting here is that if you look at the right-hand column, you're now able to pass in side information, right? Now you can guide the diffusion model by passing another image, a text, or a graphical map of a representation, and help the denoiser do a better job of kind of figuring out what to remove in terms of noise, right? So this is kind of called the conditioning or the guide. So, and the other thing that's really interesting here is that there is a smarter scheduler for how much noise to add at different steps to improve the learning process. You can add the same amount of Gaussian noise, but sometimes it's better to add more at the front. Sometimes it's better to add more at the back, further into the time steps, right? So this lower line here, the QKV, is called a cross-attention. We know about attention mechanism in transformers. There's self-attention, attention, and this is cross-attention. It's cross-attention because this is no longer attending to the pixels, the original input. It's attending to the conditioning, right? And so we will actually look at how that's done. So we know about convolutional neural networks, right? In a way, this is a super localized attention because each convolution will only look at a local patch, right? Then we have self-attention, where each pixel can actually figure out which pixels in the entire image is important, right? So in any kind of attention mechanism, typically we have three matrices. One's Q, one's K, one's V, right? Q represents the original, and then when you multiply Q and K, you're kind of learning the similarity or the importance of other pixels to this particular one you're looking at right now, right? So V, I kind of consider the strength of the signal, right? So let's say there's a strong ear in the image, and if there's a ear, there's probably eye, somewhere around here. But if there's no, it's true, ears and eyes are typically related, but if there's no ear, then, the eye is not that important kind of idea. You know what I mean? Anyways, so then what is cross-attention, right? It's looking at global relations, but now it's looking at side information or conditional information. So let's take that same pixel again in the middle of the horse. Instead of looking at which other pixels are also a part of the horse, is now going to attend to the conditional information you're passing in, which is the prompt. So let's say someone trying to use this diffusion model said, Ashran riding a brown horse. It's going to kind of really focus on the horse part and maybe also pay some attention to the brown part, right? So this is cross-attention now. And so let's then talk about Dream Boost, right? Dream Boost is an addition to diffusion models. I think this is a very efficient few-shot learning way of fine-tuning your model, right? So you're able to now inject a specific instance of a subject without catastrophic forgetting of semantics. So there's two major innovations here in this paper that I found really cool. One is that how do you indicate to the model, hey, I want you to represent this specific dog or cat, because it knows about cats and dogs in general, but I want my dog to wear a cape, right? I want you to generate that. I don't care about other dogs wearing capes. And then there's also a loss function. Loss function, again, that's very important. It's called class-specific prior preservation loss. And this kind of helps the model fix the catastrophic forgetting problem, right? So what happens here is that as the model is learning new information, sometimes it will wipe out information it's learned about general faces or dogs. We don't want that. We still wanted to know a dog has 4 legs and a dog can sometimes swim and they like to eat kibbles. But I also wanted to learn about my specific dog, right? Maybe who likes kibble less. So how do we figure out how to add a token to identify, I want my specific dog? This is a unique instance of the general dogs this model knows about. So if you use the word unique or special, right, there's too much prior associated with that word, and there's too much to unlearn. Therefore, the model really struggles with that, right? If you then go the other way and say, hey, I'm just going to use a UUID, that's a good idea, but it also doesn't work because what happens is the model tokenizes by characters, and it's going to strongly attach the word X or Y, or it's going to be completely nonsensical. So there's either too much to unlearn or too much to learn again, so it's also ineffective. So what they did is they actually did a token inversion. They found the rare tokens that don't show up as much but has some kind of semantic information, and they turn it back into the English domain, right? And usually they're finding using 1 to 3 characters works really well. And their favorite is SKS, right? So if you see SKS in diffusion models or in DreamBoost kind of settings, that's just the token saying, I want this specific dog or this specific instance. Anyways, so this slide is a little scary, but it's actually very easy to explain. Like I said, as you're fine-tuning models, sometimes you will wipe out important information about the general class it's learned earlier, right? Maybe I'm trying to make my face more tanned, or I don't know, look nicer with sunglasses. Then it may forget information about the faces in general. I don't want that. So I'm going to ask it to do 2 things using the loss function. Not only am I going to ask it to reconstruct my face, I'm also going to use the model, but I lock all the ways and make sure it doesn't learn, right? I'm going to say, hey, generate faces, maybe faces with sunglasses, and I want you to also make sure your newly generated image not only looks like my face, but also looks like the other faces that have sunglasses. So you're essentially doing self-supervision now. You're making the model generate labels to train itself, right? So this is pretty cool. The line on top, crazy mathematics, all it says is that, hey, please generate new images like this specific instance. And the crazy math on the bottom, all that's saying is that, hey, please generate new images like what you already learned about dogs in general, right? So I want you to learn about me, but I also don't want you to forget. Once again, loss function, very important for machine learning. A lot of ingenuity comes from this part, right? Cool. How are we doing for time? OK, we're doing OK. So how about a little bit of code? Ooh, this is not good. I don't know how to share this tab. Can I do this? Oh, it is maybe working. 1 sec. Technical difficulties here. Gonna see if I can mirror. Okay. I think it might be working. Shall we give this a shot? Okay, cool. I prepared a nice notebook for y'all, but I was having some terrible environmental issues, so I had to start from scratch. So this is why this still says Model Garden, PyTorch Diffusion. But this is actually what my work is based on. So you can use the same exact notebook, do exactly the same thing, right? No big deal. So what we're doing here is actually we're going to run some code to install certain environments into Google Colab. This is the part that wasn't working very well for my other notebook, right? I have to go debug later. So I'm not going to run this code again in case something bad happens, OK? And you have the option of using Vertex AI, which allows you to run all of these pipelines and processes much faster, and you can experiment better. But we're not going to do that because I said this is going to be free, right? So we're going to run this line, which tells you what Docker images to run for the pipelines. And most of this code is based on Hugging Face. And here's some kind of like helper functions that we're running. I'm just doing this to make sure the code is kind of like working. And then we're going to make it generate a kind of like AI scientist and robots helping save the forest. All right? So this will make sense a little bit later. My presentation flow is a little bit messed up now, but it's all leading up to a pretty cool point. So we're going to run this code now. And while it's running, I'll show you what's happening. So remember how I said we can provide a bit of guidance, right? Now we're providing guidance using this prompt, right? I'm saying this is what I want you to, kind of like generate. But also, I gave it an example of what I think you should kind of like try to mimic, right? So we're gonna, look at this image here. In a second, it will show itself anyways, but I just want you to look at like what I gave it as a guide here, right? So here's the first image, and here's the second image. AI scientists helping, robots in, saving the forest. So let's run that again. All right, we'll see what we get. By the way, I should probably tell you, I'm trying to build an app that makes a children's book and publishes it for Brie, all right? It's all going to happen in this notebook. I'm going to let that run, but I'll show you like what the general story arc is like. So, yeah, I know I probably shouldn't scroll that down, but like, So the story goes, a baby raccoon lives in the woods and is chasing butterflies and wildflowers. And one day, a forest fire came and took the butterflies away, and there's also no more flowers. Right? Y'all were in New York, I was in Canada, we had that fire, you guys were smoggy, I'm sorry. And then, so the baby raccoon asked humans and AI to help, and they're the guardians of the land, air, and waters, right? This is the image we're trying to generate. So now I want you to clap if you like this image, and boo if you don't like this image. Should we keep this or not? Okay, that's definitely way more boo than yay, so we're gonna run this again. See, this is the beauty of AI. We can do this all day until we're happy, right? Yeah. So we can even be more demanding, make it generate 80, and then select our favorite one. But that's gonna be a little bit hard to demo, so we're just gonna do this for now. So let's see what we get here. Taking a little bit of time, stressing me out. Okay. This is like probably the first AI crowdsourced children's book. So y'all are part of the creation team. So feel free to provide your opinion here, right? Boo or yay? Okay. All right. And then I want to have a happy ending, right? I want the baby raccoon to be eating strawberries and wildflowers and all that. So this is what I had before, but we're gonna run another one, all right? Just because I want to like make it actually crowdsourced. So we're gonna see what we have, and once again, boo or yay, let me know how you feel. We're all co-authors. There will be royalties. Okay, that one I don't know. I don't know about this one. This one looks a little bit too happy. All right. So we'll try another one here. Yeah. And the thing is, like with generative AI, you can't really tell what it's going to come up with, right? We know about these issues around hallucination and everything. So that's a yay. All right, cool. So I personally saw this one was pretty good. That's why I saved it, but that's okay. Doing a little cherry picking here. So right now, I'm just downloading a bunch of fonts because you kind of have to have text. This actually took me the longest time. And this is kind of the text, right, for the book. And then so I'm going to just run this line now and show you what the text looks like, right? I'm just making an image and adding text, right? All this code will be available to you later if you want it. And then here, I'm just saying, hey, stitch all these images into a PDF, and then save the file, right? So I'm going to say test, override my previous one, no big deal. Here, I went to a few different APIs because I love APIs for prototyping experimentation, and I got the API keys. I already put it into the system, so you don't have to see it. And here, I'm going to make a new branch, all right? So I'm going to commit this to, I think I'm on probably 8 now, so we'll just do 8. I'm going to commit this to my GitHub. Hopefully this works. OK, so we're now at M8. And now this is the cool part. I hope this still works. So 8. OK, so I want to test this first, because sometimes this doesn't work. It's looking good. Oh, look, we have our first crowdsourced AI-generated children's book. This is the one y'all chose, so don't. All right. So if you want to take a photo of the URL and say you today created an AI-generated, crowdsourced, first ever in the world children's book, you can. All right. So there's more code here, but this code doesn't really run well on my computer, and also I didn't have time to redo this part, but it is all available, right? So this is where you deploy this model and notebook to a Vertex AI instance. Most of the work is already done for you. This is literally hit and run, right? And then you can basically fine-tune a model. You can provide your own instance of a raccoon, or one that's maybe cuter than one that my friend chose, right, in the original texts. But yeah, so this is kind of where we're at. So let's go back to my slides. I think I might have to, oh no. I'm just going to do this for now. Is this working? It's just syncing, I think. OK, so we talked about AI's lower barrier to entry, right? There's a lot of cool things you can do. So I kind of want to give you a challenge and ask you some questions, right? I want you to build force and prosper. There's just so much opportunity, so many problems to be solved, right? So how will you use generative AI to create a magnificent future? A future that you want to be a part of, a future that's better for our kids, right? And what problems will AI enable you to solve? And finally, don't be evil. With great power comes great responsibility. And please, on my behalf, remember the trees, berries, and flowers. This is the end of my presentation. We may have time for questions. I don't know if anyone's interested or comments in general. Yes?
Is that Jupyter Notebook publicly available, or was that just for demo?
It will be. So what's happening now is I had to emergency fix a standard version, so I didn't even have time to save it. Because if I save it, I'll have to rerun the system installation. But I will make a copy of this, and I will make the link available. Is that all right? Yeah. Cool. All right. Anybody else have questions? I see one hand up there. Yep. Lady in the black shirt.
Hello, Maddie. To start off with an unrelevant note, it was nice to see you again.
Oh, thank you. I remember you, Annie, right?
Yep, that's me. So I got a quick question for you, and this is, for all people who would like to go beyond what they've learned from today's session. What would you say are the fundamentals that people need to know before they go off to, exploring ML and AI? Would it be data analysis?
There's lots of good things I can mention, but I think the fundamental quality is being curious and asking questions and being skeptical, right? Because AI is powerful, but it's not quite there yet. And if you kind of use it and treat it, believe it blindly, a lot of things can go wrong, right? So always keep that in mind. Actually, my friend Roya, who taught the, it's a mouthful, Google professional machine learning engineer certification with me for New York City will be giving a talk on generative AI and the possible risk and ethics. That's a really good talk. Listen to what she has to say about the gotchas, right? But as long as you keep those things in mind, the world is your oyster. All of this, play around with it, change the code. That's exactly what I did, right? I took a notebook. I said, hey, my friend wants to do this. I think this is how I can get it done. I didn't write most of the code myself. I just, took something and played around with it, right? Now, if I wanted to further improve the model, improve efficiency, make it more performant, make it use less resources, that requires understanding how these models work, right? So I encourage you to take the little breadcrumbs I dropped and actually dig into the paper and look at the code at the same time. Because for me, I'm a research engineer by trade, right? To me, until I can replicate the same thing in code, I'm not sure if I actually understood it or not. So don't be shy. AI is mostly a participation sport. So the more you do, the more you code, the better you tend to get faster. All right? Yeah.
Thank you.
Any other questions, and we still have a little bit of time? Yes, please.
Yeah, my question is about the photos that you just showed, like when photos are getting spoiled and then to find with the codes that actually, if it's the real one, I mean, to go to the initial photo. So there are also these portraits that not real human being portraits. So I just wanted to know that if this can be applied to that as well. I mean, can we find it if it's real person's photo or not with this code or not?
Yeah, so that's a really good question, and you brought up a very important risk, right? So how do we protect, intellectual property of, artists, right? I have a lot of artist friends. How do we know if this is fake news or not, right? So Google has been working on a standard, and I think this is a good idea to inject a machine-readable watermark into all the images generated by these models, right? That way, when you look at it, you don't need to know it's ugly and there's a watermark and this is, BART version 21, whatever, or, Stable Diffusion 2.1. But other models will be able to know, right? Because there is a potential for interesting feedback loop here. Back in the day, I was working in finance. I was studying for my CFA and all that. And all the algorithmic trading bots, when they had a problem, one bot made a mistake and sold a bunch of shares, and then that lead to a drop in the share price. All the other bots saw that was a signal and started to sell as well, right? So from that, I remembered about this whole AI learning from AI situation. If models keep learning from other models that's been generating things, and these models are prone to be biased because the data they're ingesting created by humans and our flawed past and our evolving understanding may be biased, this will definitely cause a problem in exacerbating bias, right? So this is why the field of AI ethics is very important, whether you're in AI or not. And this is why I encourage all of you to understand a little bit about how AI works. So if you see something that isn't quite right, you have the ability or the confidence or a way to say, hey, this ain't right, and this is a problem, right? So yeah, does that answer your question? Okay. Maybe one more question. Maybe somewhere in the back corner. It's a little bit hard to see with the light in my eye, but I feel like I've been covering this slide pretty good. And I'll be around. If you have questions, feel free to come and ask me. Happy to talk about ML or nature or camping or anything like that.
I'll project. Hi, Maddie. Great talk. I have a very interesting question. I've noticed a lot of four-panel comics generated by AI, and it seems to get the text, the punchline, it's always wrong. And as someone who's doing a lot of generative AI with imaging, I'm just curious as to why and how the technology is going to close that gap in the future.
I'm not familiar with that domain, so I haven't really experienced that personally, but I think it may have to do with kind of understanding the spatial relationships in a four-panel manga or animation, right? Because in most cases, you have the prompt, which is directly underneath for each image, and maybe the model just hasn't seen enough of the four-panel kind of setup. So that's one possibility. So if that were my hypothesis, the way I would test that is I would actually make it generate each panel by itself, right, in sequence. And if that fixes the problem, it gives me a little more confidence that is what's causing the problem. But off the top of my head, there could be a number of other possible hypotheses, right? So this is why when I mentioned earlier, when you're doing research, you want to rank your experiments by kind of like ROI. What is my strongest hypothesis, suspicion? And if it's true, that will lead to the most improvement. And then how easy is it to test it, right? So that one seems pretty easy to test, and I challenge you to, give it a try.
Thank you.
Awesome. Anyways, thank you so much for your time, and happy to, chat with you after.